Hello and welcome again to our channel Artezmia for another video about electronics. In this episode we will continue with a laser tripwire alarm, but this time we enter a new world, microcontrollers. Our alarm will send a message to your smartphone when triggered. We still have the siren and strobe lights, but the latter will be controlled by the microcontroller and we will get rid of the flip-flop circuit. We chose to use a WeMOS D1 Mini microcontroller. Why this choice? A very small footprint, very low cost, less than $2 plus shipping, and ease of programming. This video is a continuation of the previous ones we made on the same topic, but for those of you who didn't watch them, this one is standalone and we will repeat some of the sections we already covered in previous episodes, so please bear with me. The principle of the device is we have two laser beams focusing on two light-dependent resistors or LDRs in series, and when both beams are crossed at the same time, an alarm will sound and strobe lights will flash. And what is new in this video is that the message will be sent to your smartphone. As in the previous videos, the circuit has been drawn using Inkscape and can be downloaded from my website. Direction in the comments below. Here's the circuit. We're using a 12 volt 1 amp power supply that can deliver up to 1.4 amp if needed. We could reduce the size of our board if we used a barrel jack power adapter, but this would increase the cost and we might reduce the size of our board by maybe 20%, 25%, stretching a bit. We would have to rearrange the topography of our board. I did not want to solder anything to the microcontroller apart from the headers, of course, so I used female headers with long pins to go through the board, and I used some hot glue to keep them in place when no solder was needed. The microcontroller with male headers just plugs in. I can thus unplug the D1 and modify the software easily away from the board. It's a lot more practical. These headers all come with the D1 Mini. This is a picture of the D1 Mini with its headers as it comes out of the bag. Notice that this is a D1 Mini version 4 that comes with a USB Type-C socket. The one I used in this project was a D1 Mini version 3 with a micro USB socket. Here's the bill of materials. You can see it on my webpage. The core of the alarm is as previously an NE555P timer. Pin 1 goes to the ground, pin 4 and 8 go to 12 volts, pin 5 goes to ground through a 10 nanofarad ceramics capacitor, pin 2 goes to the LDRs on the high side and to ground through a 10K resistor on the low side. Pin 6 and 7 are shorted. On the high side they go to 12 volts through a 1 megohm potentiometer, and on the low side to ground through a 100 microfarad 25 volt electrolytic capacitor. This is a change from our previous design. We replaced the 1 megohm resistor with a 1 megohm trim pot so we can regulate the duration of the alarm when triggered. The formula, I'll remind you, is T times in second equals R in ohms times C in farads. The maximum duration of the alarm, as I have designed it, is 110 seconds, and we can reduce it to whatever we want with the trim pot. Should you want to increase the duration, you can choose a greater pot or add a resistor in series with the 1 megohm trim pot that's already there. Pin 3 goes to the gate of the MOSFET. In order to maintain everything at the same level of ground, we replaced the N-channel MOSFET that we had before on the low side with a P-channel on the high side. We used an NDP6020P MOSFET, mostly because it's the only one we have on hand and that has a through hole. It is not necessarily the best available, but it does the trick. The size of the board as it is 10.4 by 9.5 centimeters. Rearranging the topography, I could probably reduce it to 9 by 9.5 or even lower, rethinking the design. The gate of the MOSFET also goes to 12 volts through a pull-up resistor. When the alarm is triggered, the MOSFET starts conducting and current goes to an adjustable buck converter to reduce the voltage to power our D1 Mini and the relay module at 5 volts, or actually we have 5.2 volts, but this is fine. It's quite difficult to regulate the buck converter. We used a buck converter and not a voltage regulator for the efficiency and for the fact that the microcontroller draws quite a lot of current when powered up. The 5 volt output of the buck converter and ground are used to power the microcontroller with a micro USB male plug and to power the relay module. Here's a short clip of our breadboard functioning, just so that if anyone was not convinced yet that makers should go beyond the breadboard stage when they show their projects, now they should be convinced. How in the world would you place this somewhere and have your family believe this is a working laser tripwire alarm? On the breadboard, I have only one LDR and I have omitted the power LEDs. Here's a picture of the board top side. Notice that the siren will be connected to our board with a JST connector, a little bit easier than solder loose wires. Pin 5 and 7 of the microcontroller will activate the relays, but output pins of the D1 follow a 3.3 volt logic and the relays need 5 volts. We're using a logic level converter, or LLC, that is powered with 3.3 volt. Of course, the LLC has to be connected to ground also, and the output pins of the LLC will be the signals to the relays. Here's a picture of the bottom side of the board. Red is for 12 volts, black and green for ground. White is the connection between the output pins of the LLC to the relay module. Yellow and blue don't mean anything except that they are neither 12 volts nor ground. I'm going to include a few clips that will show voltage at different places when the alarm is triggered. First, voltage at the siren pins. Now, the voltage between the positive and negative pins of the relay module. Now the voltage between the positive and signal pins, one and then the other of the relay module. Now I'll talk about the microcontroller. The code can be found on my webpage, address in the comments. I use Platform I/O with the Arduino environment. The same code should work with the Arduino IDE. I'm not a fan of Arduino programming as it lets you get away with horrible coding. Unfortunately, the Wemos D1 Mini is not supported by Platform I/O with the ESP IDF, so I went with the next best thing. To send a message to your smartphone, I use the Telegram app. On my webpage, I give the reference of a good article and video about how to go about it. There's also a way with the Signal app, which is a lot easier but requires you to show your phone number in the code, and worse, the message is sent a few hours after the event being the alarm being triggered. Not very useful in my mind. I believe there's a way to send a message to WhatsApp, but I do not use WhatsApp, so I cannot comment on this. We get the 3.3 volts out of the 5 volts output of the buck converter. A line is fed to a low voltage regulator LDO, namely an MCP1700-3302E. It needs two 10 microfarad ceramics capacitors, one between VIN and ground and one between VOUT and ground. I'm thinking of it right now. We probably could power our LLC from an output pin of the D1 Mini, the LLC being the only item powered by 3.3 volts on the whole board. Now the real thing on my bench. Only one laser is focused, as both beams need to be interrupted to trigger the alarm, so I can prove the test with just one beam. If you set your phone properly, you can have alerts waking up the screen by the Telegram app. I set mine such that only this bot is unmuted, so my home screen is not polluted by hundreds of Telegram messages from all sources. My experience with the system is that the message sometimes appears almost instantly, sometimes with about 20-second or 30-second delay, which is still acceptable. A few remarks about Platform IO. I use a Linux Debian up-to-date computer, so if you are a Windows user, I can't really help. When you start using Platform IO, you may see an error message when building your code saying you have to update the 99 UDEV rules, even though you know and check that they are up to date. Just do a Platform IO upgrade within the app and the problem is solved. The error message will look like CMake something is not find the file. There's no fix for this error because it is not really an error. What is required happens to be done at upload time, and you can safely ignore the error message. For the UDEV rules, add yourself in the dial out in plugdev groups. I do show you how to do that and what commands to use on the command line on my webpage. As I was editing this video, several things came to my mind on how to improve this alarm system. There are some minor topographical arrangements to be made. I could find a more suitable MOSFET and use another microcontroller. I loved working with the D1 Mini, except in two aspects. Headers are not soldered when you get it, but it's good practice, and you have to use the Arduino framework, which leads to really bad code. I will look into other boards that have the same footprint, but programmed with the ESP8266 within Platform IO. This is it for now. Thank you for watching this video up to the end. If you liked it or even found it remotely useful, please hit the like button. Please leave comments below and subscribe. Stay tuned for a follow-up episode soon.